Are you ready to kick it off?
1 minute till.
1 minute till?
You were jumping the gun.
I'm jumping the gun. We're all going to roll in the door in 1 minute.
So like, well, we're not going to her off anything because she's
I think you know, and I'm already in one of the I read one time to book it.
something. Remember, if you kill them, I'm sure you okay. I'll be sure that I just said that.
There's some negative.
Yeah, I think that's a positive thing to say. Guess if bats, you're out with it.
Okie dokie. So, in case you don't know where you are, this is the St. Louis Ruby Meetup Group. In case you walked in on the street, I'm Chris Gore, and I'm going to talk to you about Lambda Calculus. And what I'm going to use to describe it is Ruby, because I'm assuming that you probably have some familiarity with it. And it's really difficult sometimes to explain math unless there's a different analog, and English is really a bad analog for most math. But computer science is sometimes a decent analog for math, especially when it's about computation. So my bachelor's is actually in math, and I love math. It's fun. It's great. Math is not doing your taxes. That's arithmetic, and hardly even that. Math is really about discovering patterns. If you want to know what math is, look at a fractal. That's mathematics. That's what mathematics is really supposed to be about. It's supposed to be about finding beauty, finding similarities, finding flow in the universe. And it's the simplest way to talk about whatever you're talking about. And if it seems complicated, it's because it's discussing something that's actually a complicated subject. It's not that the math is complicated, it's that what it's talking about is complicated. And it's usually pretty distilled. Now that makes it kind of confusing because you have it shrunk down to the tiniest little nugget that describes what you're trying to talk about. But it can also be confusing because math has some really bad notation. You know, our current notation dates back to the 1700s and it needs some work. There's some really bad textbooks out there. Then there's some really bad teachers out there. And sometimes you're the problem. But most people know. So computer science is also mathematics. Computer programming is not computer science. And you'll sometimes hear arguments that, well, therefore computer programmers should not study computer science. Well, that's not true either. Because that's kind of like saying engineers shouldn't study physics. Well, you know, somebody driving down a bridge kind of appreciates if the engineer understands a little bit about physics, just a little bit. And it's not software engineering. And even better, it's not science. It's better than that. It's math. Math is better than science.
That should be a t-shirt with like a greater than sign.
Yeah.
Science.
It'll be awesome. It probably exists. I need to get one. I'll wear it next time.
Limited press.
Limited press. No, it's probably pretty well published. Computer science, what computer science actually is that it's a branch of mathematics that describes not computers and not computer programming, but computation, which is what computers do. And what you write a program, you're making computation happen. And computer science actually is describing the very concept of computation happening. Lambda calculus. So there's the word calculus, and lots of people think instantly calculus, oh, okay, I'm going to integrate some things, or differentiate some things, or find the area under some curve, or make a bridge, or whatever I'm going to do. Well, the thing is so you're used to algebra, and there's calculus, right? Well, there's actually an infinite number of algebras, and there's an infinite number of calculi. And the one that you get taught in calculus class, that's one of them. Here's another one. It's called Lambda Calculus. The reason why this was made is to discuss computation, and even though it's complicated, it's actually a lot simpler than a lot of the other ways to discuss these kind of things. Mostly Turing machines. Turing machines are a real pain to actually try and do anything with. This is so simple and so compact that you can very quickly, it's just basically, the simpler a system is, the easier it is to think about it, do proofs with it, all that kind of stuff. And the guy who made it is this guy right here, Alonzo Church. He also invented church numerals, which we'll discuss here a little bit. Church booleans, they're both named after him. Lambda calculus, for some reason, is not called church calculus, but there you go. Lambda calculus, as I said, it's really small. It's really small. It's these. That's it. That's lambda calculus. This is just some words to help explain. 3 tiny little equations, and you've got lambda calculus. And since we've already seen all of lambda calculus, I guess we're done, right? Yay. No, not really. Because it's, like I said, math can sometimes be dense, and this is intentionally as dense as you can get computation. So let's talk through these things. So first off, some background information about lambda calculus. So it is the smallest way you can discuss programming, and it is and because of that, it's actually the smallest universal programming language that there is. Church, he made it up in the 1930s, and later on some work after that. It's Turing complete because it is a programming language. It's a full-fledged programming language. And it only has one thing that it does, and that is variable substitution to do transformations. That's all it does. There's nothing else it's capable of doing. But that's all you need, so it's okay. So if we go back to this slide, you see there's it's basically just 3 definitions: what an expression is, what a function is, and what an application is. And if you see an expression's it's either a name, a function, or an application, right? So, well, let's talk about names. Names are the easiest part. It's basically just like a symbol in Ruby. And because mathematicians can't agree on how to talk about things, it's got other names. Names have other names. Among those names for names are names, variables, and atoms. Tokens are also used, and you'll invariably run into a few more, just to be extra clear. That's the way we do things. Yeah. So yeah, symbols in Ruby are basically a kind of an analog to names in lambda calculus. Expressions. That's the big deal right here. Expressions are everything in lambda calculus. If we're talking about a name, if we're talking about a function, if we're talking about an application, those are all expressions. So it basically covers everything that exists in this little language. So if we go about a function, right? We've all used functions when we write code, and the functions here, they're also called abstractions. But basically what's happening is it's a pure function. So it's entirely all this thing is doing is taking in some inputs and transforming it and spitting it out. There's no side effects. There's no, not going to be a println. There's not going to be any like twiddling some memory on the background. There's going to be none of that kind of stuff. So, and the syntax we use is this kind of thing. So here we're defining a function that takes in a name and it maps to some expression. And it can be any name and it can go to any expression. And as we already said, expressions are literally everything. So basically, you can go in a function from a single name to literally everything in Lambda Calculus. The name part is called the argument, and that's a common term also in programming, is you call them the arguments to your function, or parameters, or there's other terms. And all of those terms will be used in Lambda Calculus too, just by relating it to each other. The expression that it maps into, that's the body of the function. And that kind of makes sense too if you think about, you often, when you're programming, you'll call that the body of your function, the stuff that actually happens in the function. Pretty much all the syntax that's actually in Lambda Calculus is just for functions. You have the lambda and the period. And that's just to say I'm starting a function and I'm separating the name from the expression. And Ruby is actually pretty good to explain what's actually going on here because of anonymous lambdas. So the basic translation of that is a stabby lambda like that, where you just are taking a single variable n and you do some expression e on it. A few other kind of irritating things. Oh, well, that's next. So the applications, the main point of applications is so that expressions can kind of blossom out like a tree. That's the real purpose of it. But applications are what you're doing with functions. You apply a function to an expression, and therefore you do the substitution. So, like, so what you typically are actually doing in Lambda Calculus is you'll have a function over on this side, and you'll have some expression, and you apply that function to that expression. And that's the actual operation that's going on. And that's function application is all of the real computation that's happening in the system. It's basically you take some expression, you apply a function to it, and then you've generated a new expression, which you typically apply a new function to and generate a new expression. So you can use parens to give yourself some clarity, but if you don't have parens, it uses the left association rule. So say you had 3 expressions, right? Well, if you just had 2, right, we already said you'd have this expression applied to this expression, right? So if you have E1, E2, E3, you do this for word first. So first you apply this to this, then you have a new expression, and you can then apply this expression to the third, and of course this chains to however many expressions you've got. It's kind of weird how this works until you get some real practice with it. And if something's unclear, if you actually were trying to walk through some worked out examples, typically the best thing to do is just put parens and map it out, because it makes it really terse, but sometimes it makes it too terse and you're just confused as to what's going on. But once you get used to it, it's nice. So simplest function we can do, right? Well, probably the second simplest function I guess we can do. Identity. You just take what you have and pass it through. It sounds like a useless function, but it's actually really not. Ruby has identity, I believe, right? Well, if not, it's easy to write because it's just that's all there is to it. It's just a stabby lambda that takes in x and spits out x again. So when we actually write out an application of a function to an expression, so say we wanted to apply the identity to, so here's the identity function. We wanted to apply it to y. The syntax that you usually use is these brackets notation. And what you're doing there is you're saying, now there's 2 forms of this. And what you're saying is basically, for every x in the expression that follows, stick a y there. Because what you're doing is you're applying this, and you're sticking in that. And of course that becomes y. because it just passes through. And just to confuse you, there's a backwards notation as well. Depending on, about half the books use this, and about the other half of the books use that. So, as of yesterday, the Wikipedia page uses this one, which I don't like. And I'm sure tomorrow it'll be the other way around, because that's Wikipedia. So, how would you do this application in Ruby? It's still pretty simple, right? So you've got your stabby lambda right here. That's your identity function, and that just passes through whatever. And you just pass it in some sort of name, like y. And since all this is doing is passing it through, you get the y spit back out. So super simple. Now, some more terms. We've got the function, I mean the name that's here is known as a bound variable because it's actually going to be changing inside the body. It's bound to something coming in from the expression that it gets applied to. The y here, that's a free variable because there's nothing over here messing with it. And here is got to be one of the most confusing things. It goes all the way back to, where is it at? This guy, right? So, you know, in each algebraic expression, you typically have x or y or theta or whatever, and it's going to change, and that's okay. But that's nothing compared to how confusing this is. This x has nothing to do with this x at all. The left side of the expression's x is completely separate from the right-hand sides of the expression's x, and that really sucks a lot, as you can imagine. And you'll, especially if you have a, you know, it's a little bit confusing, and it's just two incredibly simple expressions. You can just imagine if it was something complicated. So what you typically do in that case is what's known as an alpha reduction, but we'll talk about that later. So being as simple as it is, one of the things you can't do is you can't even name your functions at all in Lambda Calculus. There's just no way to do it. It's just not part of the language. But since this is typically something you do on paper, that's not a problem because you'll just say, you know, I is the identity function. And the syntax is typically capital, bold-faced, or double-struck letters, depending on, you know, or blackboard bold. So you'll see this, but it's not actually part of Lambda Calculus. In actual Lambda Calculus, you're going to have to actually expand all of this out manually, every single step, which is kind of irritating. The other irritating thing is there's only ever one argument to a function. There's never 2, there's never 5, there's never 0, there's always just 1. And how we get around that is we do currying, which if you've been exposed to functional programming, you've probably seen some currying before. But here it's absolutely necessary to get anything done. And so we'll talk about currying in just a little bit. Okay, so alpha equivalence. This is basically what you do whenever you have variables in expressions that match up. You just switch them out because they're completely equivalent. So this identity function here, I'm defining it in terms of x, but that doesn't mean anything. I can use y, or z, or smiley, or whatever I want. So if I had an expression like this, right, that's got, I'm applying it to y, but there's already a y inside here. The easiest way to handle it is you get rid of one of the y's. So in here, I've just switched out the y with a w, and then I'm not going to run into as much confusion because of that. Now, what's kind of weird is then you might get a production that, you know, you might get some letter, you might get w instead of y, but it's actually equivalent in some strange way because it's not about the symbols that get produced, it's about the flow. It's about the computation, not what gets computed. And that's one of the things that's really weird about this, coming from, you know, when you program a computer, you're usually trying to make something happen to something. And when you're doing lambda calculus, you're not really concerned with that. You're more concerned with things are happening. There's this flow, there's this circuit, there's this. You're more interested in the movement than the result. So it's okay if it ends up popping out as a W instead of a Y, because that's not the objective. Is to the outcome is not what you're really interested in. So beta reductions are basically what you're doing when you're trying to do the reduction, when you're trying to do the when you're trying to do these bracketing notation. That's basically a beta reduction. And here's the other syntax that I was talking about. So if you actually pull up the Wikipedia page, you'll see this like that, right? And here's another irritating thing: is it's on the other side of the equation, or the other side of the t. So what we're saying here is I've got this function that turns the input, and instead it just returns t on an s. Well, we can say either replace all x's with s like this on t, or we can say on t replace all x's with s. The nice thing about this is it kind of looks like the old style assignments in, I think it was that Pascal that looked like this? Yeah.
What's the difference between beta reduction and application?
Well, the application is technically what's going on here. You're applying this function, or you're applying this expression to this expression, right? The reduction is the process of the substitution. Is when you reduce the expression to a different expression. It's basically a way to produce. It's basically saying you can do this and get something out of it and get an equivalent expression. You reduce one expression to a different expression. The application, so yeah, application is basically an application is just two expressions side by side, and one gets applied to the other. The reduction is a way to turn an application into a different expression. So basically doing the replacement, that's the reduction. The expression is just having them sitting there side by side. And if you actually were in a class, you'd be doing a lot of beta reductions, a lot of just manipulations, just basically like arithmetic, and just hating yourself while you're doing it. So here's a very short example that I stole from the internet because I didn't want to actually have to work one out on my own. And that's actually pretty simple. And basically what you're seeing here is that all of this nonsense is this. Let me see if I can actually select this. All of this, do it, I tell you. All of the stuff to the left of this x that I can't select is equivalent to identity. Right down there. And you've reduced it through beta reductions. Well, actually, this part is the beta reduction, and then you get an equivalence, and then a beta reduction, and then an equivalence, and so on and so forth. Then you're like, oh, all this nonsense is just identity. Okay. And since wherever I stole this from the internet, this guy on GitHub used the kind I don't like, I reformatted it. Yeah, there you go. And again, you still find its identity. Okay, so like I said, there's only ever one, and no more or no less than one arguments going into a function here in the Lambda calculus. So we use currying. And what is currying? Well, it's not actually a feature of Lambda calculus. It's just a convention, just like using those bold struck eyes. And the concept is, well, if I want two arguments for my function, I'll just write this, and I'll know what I actually mean is I have a function that spits out a function, which sounds a little confusing, but it's not really, because honestly, everything in this is a function. There is nothing that's not a function in this entire thing. And so your first argument is the argument for the first function, and the second argument is the argument for the second function. So if you have xy going to y, what you actually have is x going to y going to y. And that actually works. So, surprisingly. Now, curry isn't just in Indian restaurants, it's also in Ruby. And what's actually going on is, so here's some example code. This is basically an equivalent expression to identity. And so as you can see, if you pass it in Hausa, you get Hausa back. If you pass it in Y, you get Y back. Whatever you pass in, you get back. But there actually is, so you can do the application, but you can actually call curry in Ruby, or at least since 1.9 you can, if you're so inclined. And what you're actually doing is, when you curry, you're setting what, you're making you take a function in Ruby, and you say, okay, give me that, take that function, but give me something that takes that function, sticks a value in for the first or the leftmost argument, which in this case is the only argument, and stick that in it, and then return that function, which they can then call. So this ends up being also identity. So that's two of many ways to do currying in Ruby. One where you actually type curry. So far we haven't done any actual like logical thought or anything like that. It's just translation and just transformation. But you can easily define functions that become true and false. And again, it's a purely convention. There's no hard and fast rules here. What you end up doing is you define a function true and you define a function false, and all they do is they take two arguments, and those two arguments are two expressions. One expression to return in the case of the true case, and another expression to return in the case of the false case. And true is always returning the true case one, and false is always returning the false case one. And that's all there is to it. In Ruby, it's also really crazy, simple and short. You do the same thing. You just have a function that takes in two arguments, the true and the false, and it returns it. And as long as what you're passing this in is also a function, a lambda, it'll spit out either the true or the false, whichever one you need. And you do the same for the false. And so, for example, of what this would do is if you passed it in the true, these two things, you'd get the one that you do for the true, or vice versa for the false. And once you have that, once you have true and false, you can define logical and or not, the Boolean operations. Now, the reason why these work is because this is a function. Everything is a function, and that's why this actually works. So what this is basically saying is, give me two things, x and y, which are assumed to be either Boolean true or false. And what you basically, if x, in other words, if the first one is true, then return y, which is either true or false, which makes sense, right? Because and is, if both x and y are true, then it's true. But if x is false, it does the false thing, which is just returning a false, which is so it uses the fact that the argument that gets passed in is a function in order to even function as a function. And it's the same way for the false, right? If the first one is true, then it's just done. We're true, okay? But if you can almost see this as like if x then y else f, if x then t then true else y, right? And inversion is even simpler. It just takes in a single argument and it just says if x is true, because we know that x is a Boolean, otherwise we're not going to be doing this operation on it, then false, otherwise true. So you just switch it around. And you can do this in Ruby too. Really short definitions. So assuming you still have true and false from back here defined, you can define logical and, logical or, logical not. And I'm sticking L's in front of it because and or not, of course, are still there. So I can't rename it. and just take in 2, and assuming x, the first argument, is a function, which by convention it is, we can call it on the second argument and then false, which is also a function. So this is x is a function, y is a function, f is a function, and it knows that, and it can call it these things on the other side of the argument. Or works the same way, and not is also just incredibly simple. And so, for example, if you do logical not on true, you get the lambda back for the t, which hasn't been evaluated in this case. You'll just get lambda and then like a long serial number for the lambda is what will actually get printed. And if you do L not on false, you'll get the t back. Yeah.
So these functions have 2 arguments. So is this just shorthand for the
Yeah. Because if I were to actually have the Ruby being all like one argument, it would blow up really quickly. So I'm not so one thing you can do, and it might be fun if you're so inclined, is you can actually define, and several people have done it, a working Lambda Calculus thing, like a little, either a pile of classes or whatever, whatever suits your fancy, that is a working Lambda Calculus unit, and then you can actually use it to do stuff. It's silly, but you can do it. It might even be fun, depending on your motivation. I'm not really trying to do that. I'm basically just aiming at being like, okay, because this stuff is very terse and it's not self-explanatory at all. But if you see it down here, if you see it in the Ruby, I'm hoping you can see what's actually happening. Because yeah, if you just see this, I wouldn't get that the first time, or the second time, or the third time, or the fourth time. But if I see this, hey, I know Ruby. It's a computer. I know this one. Yeah. But yeah, this actually works as it is, which is pretty cool. But yeah, the purpose of the Ruby in these slides is not really to be useful Ruby. It's to be just to show you what's going on. Yeah. So since we've got and or not done, and we can do Boolean, let's do arithmetic. So there's no numbers in this. There's just functions applying onto functions. But that's okay, because numbers just show up everywhere you are. If it's logical thought, if it's things happening in somebody's brain, like math, numbers just happen. And this is one of those cases where numbers just happen. They just appear out of the ether, right? We can just say, let's have a 0. What's my 0 look like? Well, it's some function, z, the z function. That's my 0 function. And we need some function that's the next number, the successor, right? So basically an add 1 function, which I'm going to call my successor function, which is this s, right? So what's my 0? It's just a function that takes in a successor and a 0 function. So basically the thing you want to do, so basically you need 2 functions to use these numbers. For the first thing you need is the thing that you want to do each application for each succession, and then you need the terminating guy, the 0 guy, right? So all 0 does is 0. What does 1 do? It applies the successor to 0, because 1 is 1 more than 0. What does 2 do? It applies the successor to the successor of 0. And so forth. Forever. Yeah?
Does your 0 function matter? Because I've seen other ones looking up.
Well, in the
Yeah,
case
function.
in this case, it is, the 0 is an identity, but since this is, so here's the thing, right? Everything is a function. Everything is applicable to everything else. Every function will work as a 0 function. And that's one of the cool things. So if you want to loop, if you want to iterate, what you do is you apply a church numeral to the thing you want to loop, right? So if you gave it a 0, if you basically wanted to do something 10 times and then in the terminating condition do something else, so say you wanted to print 99 bottles of beer on the wall, and so on. And eventually, your zero condition would be we're out of beer, right? The zero functions that we're out of beer, all the rest of them are just the print n bottles of beer on the wall. And you can do this for any loop. So it's basically a loop and a terminator. So, like this. Here's church numerals in Ruby. And this actually works too. Although it took me a little bit of trouble trying to figure out how to get the actual generic one to actually realize itself. But, so, in the case of 0, I'm just defining a function that takes in a successor function and a 0 function, and all it does is the 0 function. That's basically what's going to go on. Although actually there should be a pair of brackets here. I forgot them. Yeah, well. On the 1, we apply that. And the 2, we apply that twice, and so forth, right? So the general form, here's the general form, is, now I'm cheating here, and I'm using actual integers to count down. But if you really were so inclined, you could actually make this happen with church numerals too. It would probably be a little bit longer of a slide for that. But yeah, you could have this be totally just like tied in on itself right here, and have n be a church numeral thing. So Cn takes in a church numeral here. But yeah. So basically if n is equals 0, just do the 0 function, which here I'm also, like I said, I'm passing it in no arguments. I'm assuming it takes nothing. Otherwise, what do? Give it the successor function that you passed in. Bring down n, and then do the successor on the 0 function forever. So if you have these two functions, so we're going to use the hausa as the successor function, and you have this hey as the 0 function, you're going to get printed to your screen hausa, 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 hey, if you call that. And that actually works. It just prints them 4 times, and then it brings it down and prints the last one, and then it's done. So it's an inherent loop because it's basically unrolling from the ifs. And I'm actually going to stick this in, if I can select, I'm going to stick this in Ruby because I want to see that. Where are we at? Bigger term. How do I make the font bigger on this guy? There you go. All right. Is that good? A little bit bigger? How's that?
Good.
Okay, cool. Oh, I probably actually do want to be there. Here we go. Okay, so will that work? Yep, okay. So there you go. And if I give it like just 1, there you go. You just get the 1. If you get the 0, there you go. Just the hey. 10. Anyway. So it's basically, the idea is a number, an integer number, a positive integer number, what you're actually having happen is it's the concept of a loop happening. That flow is the number. Basically, it's what's going on. And you're translating that back, and it works like a different algebra. You can pretend it's a number, and it is a number. So it's good enough. You can have all of arithmetic with this, including, well, so here's the standard definitions for your successor function, your addition, your multiplication. Your exponentiation is actually the shortest, which is pretty cool because so this is one of the things that I thought was pretty cool is, yeah, exponentiation is the easiest of them all to write because basically what's happening is you're applying a number onto a number, and that just, there you go. It just basically multiply yourself that many times. So it's the shortest of them all, which is pretty neat. Subtraction is really difficult. Well, not really difficult, but it's like I'd be up here a good 20 minutes if I wanted to even touch subtraction. Basically, what it boils down to is you need to. So you need to define instead of a successor function, you need to find a predecessor function, and that's like difficult. It's in one of the slides I reference, and one of the PDFs I reference in this slide set. Somebody goes through it. It's maybe about a page or two, but it's kind of convoluted in what you have to do to just get that thought happening, because these numbers here, they only do 0 and up. There is no negative number. There's no way to do negative numbers, and without the negative numbers, you can't easily do subtraction. But once you get that predecessor function, you can have subtraction, and then you can have negative numbers. And then, of course, you can do division after that, and so forth. Floating point numbers, well, even if you aren't limiting yourself to such a ridiculous machine as this, floating point numbers are just a real pain. I don't know if you've ever looked at like the floating point standard, whatever it is, IEEE 700 something. But if you ever have to like deal with that document and care, you are going to hate yourself for a while. I speak from personal experience there. It is not fun. Floating points are a bad idea, but they exist and they're necessary, unfortunately. But since if you have positive and negative integers, you obviously can do floating point numbers, because that's all we really have in hardware is really just a bunch of bytes, right? So it makes perfect sense that you can do it. And yeah, it's been done. I don't have a reference for that, but I'm sure if you look around, you can find it. And pretty much everything else you could possibly really want to do with this thing is a pain. It really is. The only thing that this is really good at is if you want to do proofs about computation, because you're a computer science / mathematician who likes to do proofs about things all day, then it's great. Because it's so tiny. It's just 3 tiny little equations. It just rolls in on itself everywhere. It's just perfect for that. But if you actually want to use it as a tool to get something done, yeah, it's just not the best choice.
You can actually build the primitives for Lisp out of it.
Oh, yeah.
Pretty easily.
Yeah, I saw that where somebody was doing like, yeah, they basically built the linked list, and then you want to go from there. Yeah, that was pretty cool. That was actually a lot easier than trying to do like subtraction. So.
So then you do subtraction in your new list.
Yes. Yeah. So.
Does it kind of look like Haskell? I don't know. It kind of looks like Haskell.
Well, Haskell is big.
Oh, only in the fact that it's a little bit difficult to read. Yeah. And it's useless.
Shots fired.
Yeah. What's up?
So Corey Haynes has been tweeting the past couple weeks, implementing this in Ruby, church numbers. He's got subtraction. Looks like he's working on tuples and lists right now.
Okay.
You can do lists. I think they might be called church list or something.
Yeah, well, you can do anything.
Well, there's conventions for that as well.
Yeah.
And when I was looking for that, Jim Myrick did it several years ago.
He has a really good presentation to the Y Combinator.
Oh yeah, that would be like just one talk on its own.
Yeah, that was a keynote at the Ruby conference.
Yeah, one of these. So on the GitHub repo for these slides, which are linked in the meetup, I've got some of the references I was using, and one of the really good ones was the Rojas one. I think he had. Let me make this big. There we go. No, not that big. This big. And we can't read that. Does he talk about division? Yeah, here you go. So here's the predecessor function. And then it's a little bit easier after you get that guy figured out. Is this the Y Combinator? Yeah. That is the Y Combinator. Yeah, okay, there you go. There's the Y Combinator.
Which is what you needed to get around the need for the let rec on the where you needed the.
We need to find the church rules.
Yeah.
Yeah.
You need the Y Combinator to
Any other questions? Any other comments? Any other insults to Haskell? No? All right. And here's the references that I have. That should do it.
So what else is in the Lambda Calculus each area that you haven't covered? Like you said, you mentioned Y combinators.
Oh yeah, yeah. The Y Combinator is that's just a one-liner, right here. How do I zoom that in? There we go.
Substitution line.
That's that guy. And
These
it's
are important landmarks.
oh yeah, like the vast majority of computer science. But yeah, this is like a perfect example, right? It's so tiny of a little equation, and it's just like so fundamental.
If you try to implement Ruby, that's not good things happen.
Oh, what does it do? I didn't even
will,
give it a shot.
It'll just stack overflow because it's applies the arguments first.
Yeah, we don't have tail recursion.
You have to have
TCO, tail call optimization.
well, no, it's because of the call semantics. It applies the arguments before
Before it actually calls
whether
it.
it's needed or not.
Oh, okay.
So what you actually have to do if you're going to implement in Ruby is actually put an extra layer function in there. So something more along these lines.
We can probably do the camera if you want somehow. Let me make the camera happen. Zoom will do that.
So I think this is called the Z combinator.
Start with vehicle. This work? Hi. Hi, me.
Yeah, so that
Hey,
guy,
yeah.
so it's kind of like the top part is you're taking in some function that you want to be able to have recursive. Then the first part is just duplicating like this, the bottom line. So now x is going to be this bottom function itself. And then it takes in one more argument. And then you apply f and passing in like that whole thing again. And then the one argument that you want to take as a parameter.
Cool.
So that would allow you to actually recurse without like just keep going down the like expanding out the Y combinator.
Okay. Yeah.
Does one usually learn about monads through Lambda Calculus or through something else?
I don't know. I still don't really get monads, other than like the philosophical, like Neoplatonic definition. Like the monad begat the dyad, and the dyad begat the triad, and the triad begat the tetrad, and the tetrad eventually begat the universe. I don't know. The more you go into this, the more you will do these. That's the end state of like doing this kind of stuff.
So, is it showing our age to recognize that from the Atari Basic cartridge?
It is.
Yes.
What kind of computer's on the right?
I don't know. Some just beige box on the side. Yeah.
I was just giving it a try to watch.
But the keyboard, I think I do recognize the keyboard. Oh yeah, I'll Model M.
That's
Perhaps.
quiet.
Huh?
That's in quiet means I
Anything else?